The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
Example, gravitational force 4. Okay, if an object is dropped on your foot from the same height, would it cause more pain on the surface of the Earth or the surface of the Moon? Now, the acceleration due to gravity, we just said on Earth, right? That was 9.8 meters per second squared. Now, what is the acceleration due to gravity on the Moon? Well, if we see here, the acceleration due to gravity on the Moon is 1.6 meters per second squared. That's roughly 1/6 of what the downward acceleration is on Earth, right? Thus, we can then safely say that you would feel less pain, right, on the surface of the Moon, because when the object is actually going to be making contact with your foot, it's going to be making that contact with a slower velocity, right? And because of that, it's going to be slower on the Moon, or it's going to hurt less on the Moon, and it'll hurt more on the surface of Earth. So if we just go ahead and read our question again, if an object is dropped on your foot from the same height, would it cause more pain on the surface of the Earth or the surface of the Moon? So it's going to cause more pain on the surface of the Earth. So A is our answer in that scenario. Wonderful. Now let's look at the second part of our question. If you pick up and throw the object that was on your foot in a horizontal direction, would it travel a greater distance on the surface of the Earth or the surface of the Moon? Okay, wonderful. Now let's actually think about this for a second, right? So here, let's say the object is thrown as such, perfect. Here is the initial object, here is where it lands. Now, the mass does not change, right? The mass stays the same no matter which planet you're on, right? Secondly, we're going to assume that it's thrown with the same force on both planets. Now, what does change is the acceleration, right? Because the acceleration is 6 times more downwards on Earth, right? We would anticipate that it's going to strike the surface, right? It's going to land first on Earth, so it's going to have less of a flight time on Earth. Now, because its downward acceleration is 1/6 on the Moon, we would anticipate it's going to have a longer flight time, right, on the Moon. And because it has a longer flight time, we anticipate that it's going to travel a greater distance. Thus, this is most likely, it's safe to presume that the greater distance is going to be on the Moon. With that said, greater distance on the Moon, that's B. There we go. We can safely assume that B is our answer there. Wonderful. Let's now move on and we'll do another example. Great. Example, gravitational force 4. What is the force of gravity amid 2 electrons, and the mass is 9.1 times 10 to the power of negative 31 kilograms, separated by a distance of 0.5 nanometers. Secondly, what is the force of gravity between an electron and a proton if the distance remains the same? The mass of the proton is 1.67 times 10 to the power of negative 27 kilograms. Wonderful. So on this slide, we'll tackle number 1, and then on the subsequent slide, we'll tackle number 2. Let's begin here just with our equation that we've been using thus far, and we are looking for the force of gravity amid 2 electrons. So here is electron 1, here is electron 2, right? And the distance between them, which is just going to be r squared. Now, if we go ahead and we fill in our values, well, we know that the gravitational constant is just going to be 6.67 times 10 to the power of negative 11 Newton meters square per kilogram square, and the mass of an electron, which is just 9.1 times 10 to the power of negative 31 kilograms, and we can just square that, right? Instead of having to write it twice. Wonderful. And how about R? What is R? Well, 0.5 nanometers, right? How many meters does that work out to be? For meters, that's just going to be 5.0 times 10 to the power of negative 10 meters. And we'll just square that. Wonderful. And then once you go ahead and you equate that, you find that your answer is 2.2 times 10 to the power of negative 52 newtons. And that's very small. Great. Wonderful. Now let's solve the second part of our problem on the subsequent slide.